So Women Who Code's mission is to empower diverse women to excel in technology careers. Our vision is to see a tech industry where diverse women and historically excluded people thrive at every level. Our values focus on the mission, design for inclusion, advocate for change, and journey forward. In just 10 years, we have grown to serve members in 147 countries globally. We started in 2011, and as a small community group in San Francisco, we quickly grew. Women around the world wanted to be a part of the community, and today we're a global footprint of 100,000 strong and growing. Women Who Code is an inclusive community dedicated to providing an empowering experience for everyone who participates in or supports our community. To view our full version of our code of conduct, please feel free to visit the link displayed. And with that, I'll give the stage to Neo4j.
Thank you, Diana. It's really a pleasure to be here, and thank you everyone for joining. So we're very excited to talk about Graph today. My name is Yolande Poirier, and I'm a community manager. I organize events like this, and I actually make sure that we have a presence in the community. So I'm kind of the touch point of a person for any community and technical community especially. So a few words about Neo4j. So Neo4j is really like the graph database and data science leader in the market. And I think at a very high level, and we'll get into this a lot tonight, but at a high level is graph is really essential if you want to look at relationship in complex data sets. And so we have very clear value and benefit if you, for example, if you look at social networks, for example, or anything that has like complexity in your data, it's where we find those relationships. So recommendation engines, supply chains, and it's looking at anomalies and also helping improve all the systems. So, but for Neo4j, so relationship is not just important in the product, it's also important for the culture. And I found that it may sound a little silly, but actually valuing a relationship in corporation is really important. And it really makes the life at Neo4j much more pleasant, and the work, and my coworkers, my wonderful coworkers here also, like it's really a pleasure to work with them every day. So on this note, I'm going to introduce you to my colleagues. So Katie Roberts is, she has a degree in cognitive neuroscience from Harvard University. And today she is a data scientist solution architect at Neo4j, and she helps data science team become successful with their project. Sydney Beckett, Sydney, hi. She is a senior solution engineer at Neo4j, and she was introduced to Graph as a consultant, doing a lot of consulting work with clients. And today at Neo4j, she is also helping quite a bit our clients implement Neo4j solution, and she's also doing a lot of training, so training on for customers' accounts. And Cynthia, hi, Cynthia Femano. She's also a senior solution architect, and she's been a data architect for a very long time at many big companies like CBAS and government also agencies. And she is also like hands-on at customer account, like implementing solutions that makes everybody successful. So Cynthia, handing it to you.
Hi, everyone. Thank you for your time tonight. I'm going to get started here with an obvious slide, but sometimes when we talk about graphs, some people think of charts and dashboards and things like that. So we just want to clear up when we start that we're talking about the kind of graph here on the left, which is a bunch of entities that are related to other entities. So just to clear up that confusion before we start. Graphs are everywhere. I mean, they're all around us. Everything is connected to everything else. And these are some examples of graphs. The internet is a graph because there's a lot of IP addresses connected to others. Your public transit system is a graph of stations connected to other stations and routes, supply chains, social networks, of course, Facebook, LinkedIn, chemistry. There's a lot of use of graphs in chemistry and genetics, and also access management, who has rights to see which documents, etc. So these are all examples of graphs. And graphs, one thing that graphs give to us is context or meaning. So if you have a bunch of people, there's not a lot of meaning to that, except there's a bunch of people. But like once you start to know like who's connected to who, or who knows who, or what organization they work for, or where they live, you start to get like a lot more meaning from the data than you would if those relationships weren't there. So this slide shows you a couple different types of networks of people, networks of transactions, who's buying what, how they paid, etc., where the inventory is coming from, and knowledge networks. So there's a lot of information out there, and we might want to search through it or find related information that could be of interest to us. So these are other examples of graphs. Now, why are graphs important? Well, relationships are important. And at Neo4j, we treat the relationships as like the first-class citizens. So the book Connected by James Fowler, he talks about how relationships are the biggest or the strongest predictors of behavior. And this is true because the fact that like the people that you know, or the places that you live, or things that you're connected to, can predetermine the other things about you, such as how you might vote, or if you smoke, or if you're healthy, if you're fit. So this book, if you're interested in reading more about that, it's a great book. And when we get into data science, relationships are so important. And a lot of times the way our data is organized in tables with rows and columns, we're not seeing those relationships stand out. So graphs have a lot of power when it comes to data science. This is an example about how network structure can be highly predicted. So say you're on LinkedIn and you have 300, 400, 500 connections, but they're all people within your company or maybe your friends. And then compare yourself to someone else who has maybe less connections, but those connections are pulling together different groups. So you might know someone in another company who's connected to a bunch of other people, or somebody at a university who's connected to other professors or students. So those more like inter-community connections that you have can raise the level of your influence. This study here showed that people in organizations that were connecting disparate groups within the organization tended to be more successful and more likely to get promotions and higher pay than people who were more so like in the middle of their own community but not connected with others. In fact, Gartner predicts that by the year 2025, that graph technologies will be used in 80% or more of data and analytics innovations. So this is a trend that you should be paying attention to. It's becoming more and more prevalent in the industries. So graph databases unlock new possibilities. So a lot of you out there are familiar with relational databases and how they're structured with rows and columns. And they're connected by primary foreign keys. They require joins and index lookups to find the relationships in the data. Then we go to NoSQL databases, which are even further denormalized and really don't have a way to handle relationships at all. The data is just in these wide tables and everything is on a single row. Then we look at graph databases, and graph databases natively store data as entities with pointers to other entities. So the powerfulness of the graph database is that you can see these relationships, you can query these relationships, and you don't have to do all this underlying like table joins or write a lot of code. It's pretty simple and pretty it's pretty efficient. In fact, it's so efficient that when you're doing queries that require 3, 4, 5, 6, 7 hops, those queries are going to run up to 1,000 times faster in a graph database than they would in relational or NoSQL databases. Now, there's more than one type of graph database. There's actually a lot of graph databases out there. One differentiator is that some graph databases like Neo4j are native graph databases. They were purpose-built to be graph database. So the storage layer is a graph. The compute layer is a graph. The query language is designed for querying graphs. So it's very efficient in what it does, and it's very specific, purpose-built. There's other databases on the market which are more like multi-purpose databases that can do graph also, amongst other things. Usually these databases have an underlying storage layer that's either relational or NoSQL. So there's some sort of translation layer that happens in between, and then the query language can be it could be Gremlin, Cypher, proprietary languages, but there's that extra layer of translation that from the query language into navigating the storage. And then on the far right is your relational database where everything is stored in rows and columns. Your language, query language is SQL. SQL is built for joining tables and querying data this way. So this is just like an example of the different types of databases. Now, imagine if you were solving a problem where you wanted to know how do I get to Tony's Pizzeria to get my pizza? Well, you're going to be following a path to get there, and it's going to be certain streets that are connected to other streets. You may have to take left turns, right turns, etc. Imagine trying to query that in a relational database and the number of joins that you would have to do iteratively to solve that problem. Now look at the other side where you're looking at a graph database, and it's pretty straightforward because graphs are basically paths or patterns, and you follow from one to another just by following a pointer in storage. So this is just kind of an example of like some types of queries really do lend themselves to graph databases and graph storage, and are obviously going to be more efficient in that platform. So let's move on to labeled property graph. So there are different architectures for graph databases. Neo4j's architecture is the labeled property graph. Neo4j is the inventor of the labeled property graph. If you're familiar with graph databases, you may have heard of some others out there using RDF triple stores or quad stores. They're built a little bit differently. So I'm going to explain the labeled property graph model. Labeled property graphs are made of nodes and relationships. Nodes are the entities in the graph. They're the nouns, the objects, and the relationships are the verbs or connections that connect these entities together. In Neo4j, both nodes and relationships can have properties and such, so it's a property graph. So a person could have a property or multiple properties. These properties are key value pairs. So in the example, we have a person, it has a property name, birth date, Twitter handle. Those are all properties of the node. And then we see the relationship, for example, between the person and the car. We have also a property on that which defines a start date for that relationship. So that's how a labeled property graph works. So the labels themselves are really depictors of the type of entity. So in this example, we have label person for person entities, and we have a label car for car entities. But there are many instances of persons in our graphs, and there's many instances of cars. And then with a labeled property graph, the query language that you use is called Cypher. And Cypher is, like we'd like to say, it's using ASCII art. So we're kind of drawing pictures of the paths that we want to follow, enclosing the nodes or entities in parentheses and the relationships in brackets. And then we use these arrows to depict our relationship direction. So in Neo4j, relationships are always directed. They go from one entity to another, but you can traverse those relationships in either direction. Along with Cypher, there's other ways to connect to Neo4j. Obviously, you want to be able to import data into the graph using Spark, for example, to pre-process the data. Maybe you want to grab data from your data warehouse, or maybe you want to stream data into the graph using a messaging queue. You can then, maybe you want to display the results of your query in a dashboard or visualization. So there's connectors for that. And there's Apache Arrow is also a fast way to get data into a graph. So these are various connectors that you have, and then language drivers. So you have APIs or drivers for common programming languages like Java, Python, JavaScript, etc. These allow you to interact with the graph and query the graph from an application. So that was a lot said. I think it's a good time now to maybe show you a little example of a graph with Neo4j, and I'm going to hand this over to Sid Beckett for a short demo.
All right, can everyone see my screen?
Yes.
Okay, awesome, thank you. Okay, so I am going to start with just explaining really quick that you could go to Neo4j's website, click Get Started. And what I'm going to use is our database as a service called ORDB. I'm going to use the ORDB free, so you can get started for free. Doesn't require a credit card, and you could use it for small development projects. There are other ways to get started, being able to download a Neo4j desktop version, a desktop version of Neo4j, and also using our sandboxes, which I'll talk about a little bit after this demonstration. But once I create my database in Neo4j, let me quickly point out what we're going to do. Sorry, I'm jumping around a little bit. But once we get into ORDB, they give you options. So you could start out with like a database that's already pre-populated with data, or you could have an empty instance and import your own data. Today, we're going to use the Stack Overflow database and take a look at some Stack Overflow data. When we create our instance, they give you have the ability to upload a database. If you have like a dump file or connect, they give you information on how to connect to your database. However, I'm just going to, you could just open up your database right here. And when you open up your database, you have the option to explore using Bloom, explore using browser, or there's an import capability there where you can import data directly from CSV files. So right now we are looking at Query. Query is the Neo4j browser. This is where most developers get started with Neo4j. You can import your data using the browser. You can query your data using the browser. But more importantly, you can look at, if you look to the left, you could see how many nodes and relationships are in your data, what they are, what property keys are in your database. You also have access to database functions, the ability to use role-based access control, lots of features that Neo4j has, especially when you start thinking about using Neo4j from an enterprise perspective and security starts to become important. But you have the capability of doing quite a few things through the browser. We will do a demonstration of Explorer using Bloom right after we do a little bit of work in browser first. So inside, once you, if you choose to start a database that's already pre-populated, it also comes with, sorry, I should have started from the beginning here. It also comes with browser guides. So here we're going to use the Stack Overflow browser guide. And what that does is enable you to get a little understanding of the data that you're getting ready to look at, but it also walks you through that use case using that data, providing you with the Cypher queries that you need to query the database. So if you look at this browser guide to the right, it's giving you a little information about the data, where it comes from. It talks about, in this guide, you'll be able to load some questions and answers and comments and tags and users into the graph and be able to find some unanswered questions, discover, use querying to discover engaged users and so forth. And then we click next, we'll switch to the next page. First, we could take a look at the data model here. So as Cynthia mentioned, we're not storing our data in tables and columns. We're storing our data as nodes and relationships. So when we are pulling our data into Neo4j, we're thinking about the questions that we want to get out of our data and thinking about how we should model our data to get those answers. So before since this is kind of small, I want to go ahead and take a look at the schema. So if you scroll down, we'll see our first query here. If I click edit in Cipher Editor, it puts the Cipher up in the editor here. If I just push play, it'll just run that query as well. But I wanted to show you here, I'm going to delete some of this just to show that, like I said, there are lots of different functions available in the database from DB or DBMS. Here, we're using a function that allows us to look at the schema of the data in the database. So when I run this, I'm going to close this box for a second, you could see the schema of the data that exists. So if you look over at the types of nodes that we have in our database, as Cynthia mentioned, you can use labels to define the types of nodes that you have. So these are the labels of the nodes in the database, and we have comments, we have questions, we have tags, we have answers and users. And then we have our relationships that describe how these nodes are connected. So our user could ask a question, they can provide an answer, or they can comment on a question. We could see the comments are also connected to the question because that's the comment that was commented on, and the answer is what answered the question. And also the questions have tags. These are keywords that are pulled out of the question to define what type of question or what that question may be about or related to. All right. As you move forward in the browser guide, we'll see here, there's a query here that shows you how to import your data. So if we just click on this to just kind of take a deeper look at it here. With this query, it's showing you how to call using APOC. APOC is our awesome procedures on Cipher library. It's a huge library of lots of, as it's called, awesome procedures that you could use in your Neo4j database. It's procedures like this one here, where it enables you to load JSON formatted data from a URL. There are some that allow you to load other types of data or be able to load data from a JDBC connector. There's also procedures for other things like doing things with geospatial data, maybe running, I believe, Leverstein distance. There's all kinds of procedures that are available. So that's worth checking out when you have some time. If we clicked on this, it would import some additional data, whatever is not already in our database, because we're using merge statements. I am moving a little bit fast when I talk about merge, but there is another browser guide called Movies that I strongly suggest later. Maybe not tonight because it's going to be late after we're finished, but definitely maybe over the weekend if you want to play with Neo4j, that would be the next data set that I would strongly suggest trying out. You could try that out in our browser guide or in our OraDB database. It will walk through how to create a node, how to merge a node or create a relationship. But tonight I'm going to focus on, let's see what the data looks like in Neo4j. So we're not going to run this query here. I'm just going to get rid of it. And we're going to move forward in. So as we move forward, each page provides more instructions and more Cipher queries that you could try. But before we advance any further, I do want to give an opportunity to explain a little bit more and show what Cipher looks like. So what I did is I pre-ran a few queries, mostly to make sure that I didn't have to copy and paste and take up time copying and pasting these queries. But what I did here is I created a match statement. So as Cynthia explained, We're using ASCII art. You could see the parentheses around user. You could see the brackets around asked. And if you remember our data model that we saw before, we could see user is a label in our database as a node, and we could see asked is a relationship between the user and the question. And then we can see here, we're following this pattern of tags. So now we say a user asked a question, and now we're looking for the relationship tagged, and it points to a node called tag. So we see that path right here. And so it's a lot like Cypher, a lot like SQL, and that for our select statement, you want to select what you're looking for. This is what our match statement is doing here. We're matching and we're saying we want to return this path. You also have the opportunity in Cypher to have where clauses. You can use, we'll see later on, being able to use order by. You could also use case statements, union. There's a lot of features in Cypher that you would typically find in SQL, but the critical point the critical difference is what you're actually trying to return. In this case, we're not selecting from a table and then selecting what columns we want. In this case, we're looking for a pattern in the database. So we're defining that pattern. And in this case, we want to return the path. So when we return the path, let me make this a little bit bigger so it's easier to see. We could see these paths now. We can see our users. I'm going to open this up so we could see that our users are green. So we could see our green nodes here are representing users. And then we could see our tags are orange. So here's our tags here, and we could see our questions. And so we could see now our user here, Damien, asked 3 questions, and they were all tagged with tags. 2 of his questions, or 3 of his questions, were tagged with, it looks like 2, sorry, 1, 2, are tagged with Cypher. And then we have 2 that are tagged with Neo4j, and then 1 that has some additional tags that are not related to the other questions that Damien asked. So graph, in other words, enables you to start to expand out to see what is connected beyond that. So being able to go beyond the question Damien asked and say, okay, what was tagged? And then be able to say, okay, now that I see Neo4j tagged here, what else was tagged to Neo4j? Well, we could see there's this question here that was asked from someone else. And we could see another question that was asked from this person. So we can start to see quickly who else asked questions that were very much related. Sorry, I'm losing my voice. They were very much related to Damien's question. So Graph enables you to ask those complex, highly connected questions of your data. You can go even further with your path. Here, we're looking at a user who asked a question that was answered, given an answer, but who gave that answer? Another user. What might that user have asked? So this one is running even a more complex question. It's looking at what a user asked who also answered a question for another user. So here we have a user here. Sorry, let me zoom in a little bit more. We have a user here that provided answers to answer questions from a number of different people if we look at around there. But this person also had a few questions that were asked as well. And you don't have to just return a path. You can actually take that same query that we ran before and just return properties. So in this case, I just want to know the person who asked the first question, the title of that question that was asked, the body of the answer, the person who gave that answer, and then the title of the question that that person asked. So looking at that, we would have to, let me see if I can make this bigger here. We could now see all of those properties. We could see the display name of the person asking the question, the title of the question asked, the answer, the display name of the person who answered it, along with the title of another question that that person asked. And you can define whatever pattern that you're looking for, specify or filter through for specific things using Cypher. You can export these results. This gives you an option of CSV or JSON, or if you were using some sort of API, you can return, you can send these results out to perhaps an application of some kind. So let's shrink that. All right, so let's advance a little bit more through our browser guide. So I'm not going to hit everything in the browser guide for the sake of time, because I want to get to some other fun stuff with graph data science. But there are other things you could do in here, like running Cypher to look at all of the labels in your database and the counts of those labels. Here, this query here is looking at the top tags. So if I run this by just clicking the run here, we could see those top question tags that are in the database. We could see Neo4j has the most tags in this particular data set that we pulled from Stack Overflow. And then there's some additional questions here that you could play around with. I want to point out the shortest path down here. I'm going to go ahead and run it, but there is a procedure that you can run where you're looking for, in this case, let me expand the query here. We're looking for the shortest paths between one user and another user in a database, no matter how many hops it needs to take to get from that one user to another user. In this case, we're just limited to one. So we can see this one user inverse Falcon. And then we could see this other user Alexinoid, and then we could see the path that was taken to get from one node to the other. So there are path algorithms out there. Then there's other queries here, user engagement, unanswered questions. I definitely wanted to kind of point out here, we're looking at a tag. And then there was a question that also was tagged with something else. So we're looking for those nodes that have multiple tags on it. And then we want to count how frequent these two tags are paired for questions. So in other words, how frequently do these two tags appear together for a question? And we can see Cypher and Neo4j APOC, which we used the APOC library earlier, were tagged most frequently. A nice, neat thing that you could do in Neo4j is Neo4j is schemaless. It's very easy. You don't have to design a model and then go through heartache and pain if you want to make a change to your data model. You can change your data model very easily. And in this case, we're going to run this query here and create some additional relationships really fast. And why we did this? Well, we wanted to take that same query that we just ran, where we're looking at questions that have multiple tags and how frequently these tags appear together. But we want to be able to find this really fast. We don't want to have to run this query every time and then try to define that we only want those that have a frequency that's greater than 3, because less than that is not a huge concern to us. We want to find it really fast. So what we're doing is, now that we found those two nodes that have those two tag nodes that appear frequently, more frequently than 3 times together, we're going to create a relationship between them called occurred. And on that relationship, because you can store properties on relationships in Neo4j, we're going to call that relationship frequent. And then we're going to set that equal to the number of times that they appear together. So now that we have this occurred relationship in our database, now we don't have to run that query, but we can run another query looking for our occurred relationships, and we can see that frequent relationship property now on our relationship. So as I hover over these, you can see the different amounts of frequencies that these tags appear together in the database. Okay, and there's a few other things that you could do here. Here you're looking at users who comment on the same who make comments together or similar commenters, I'm sorry, in your network. And then there's some further reading and links here as well. So I definitely suggest, like I said, going back and trying the movies demo, but now we're going to go ahead and take a look at Bloom. So Bloom takes visualization a step further. So before in the browser, we're able to look at these nodes, and sure, you could do a little bit with coloring and looking at the relationships and saying, oh, I want them to be a little bit wider or maybe a color. So there's a little bit you could do here. And then you can also expand to see all of the nodes that are attached. So here, let me close this screen here. You could see I clicked on a tag, I expanded to see everything that all of the relationships that Spring has. And we could see that there are a lot of questions that have been tagged with the word Spring. However, Bloom adds additional visualization capability. So when you click over to Bloom, you're going to have the opportunity to create a perspective. Here, we're just going to generate a perspective. What it's going to do is it's going to look at all of the nodes and relationships in a database and just pull them all into the same perspective. However, you have the opportunity to customize what nodes and relationships you want in your perspective. But Bloom enables you to query the database using your natural language. So you don't have to know Cypher. So if you've learned Cypher, but other analysts haven't learned Cypher, but you want them to have the same ability to query Neo4j as you do, they can do that through Bloom. So what we're going to do here is we're going to look for that query that we just created. We have a tag that's actually suggesting occurred because it knows that occurs in the database between tag. And this is what we want. This is the pattern we want that we just created, where there's a tag that has the occurred relationship between another tag. And we just press return. It queries the database. It finds all of those matching patterns in the database for us. And so now we could zoom in. I'm going to close this Stack Overflow so we can see this better. Now we can zoom in and see all of our relationships in our nodes. It has some additional features. If we click on tag here, not just color and size, but you can also choose icons where we could just say, I want to look for a tag and just use a tag as an icon. So there's additional things that you could do there. Another thing you could do is you could use rule-based styling. So like if I click on the relationship here and I click inspect, I can see that property frequency that we put on that relationship. But I don't want to have to look at this graph of all of these occurred relationships and have to click on each one to find out who had the most occurrences. So what we're going to do is go to our relationships. We're going to click on occurred, and we're going to use some rule-based styling here. So I'm going to find the property frequency. We could see here, it's showing us that we have some that are as low as 4 and some that are as high as 87. I'm going to say that I want to show it by range. And instead of color, I want to show it by size. So I want my smaller ones to look really small. So we're going to make it smaller, and our bigger ones to look really big. So I'm going to pick a bigger number there. And when I apply this sizing, and now when I look at my graph, I can quickly see who are those that have the largest occurrences compared to who had much smaller occurrences than others. So that makes it more visually readable and understandable for others. I'm going to clear my scene here. Another thing you can do in Bloom that's really great, especially for those who are not familiar with Cypher, is you can store a search phrase. And that could be as easy as taking the query that we ran before, and where we looked at that long pattern where we're looking at the user who asked the question, who provided an answer, who also asked a question. Sorry, I'm trying to get my copy paste my search phrase. And then we can just assign it a search phrase. And it could be anything you want, anything that's meaningful for that particular cipher query. So such that now that it's there, all we have to do is write that same search phrase, return, and now they can run the same cipher query that you had before. So that enables an analyst who's not familiar with Cypher to be able to run the same query that you did and be able to get to see the same results that you had. There are many other features in Bloom, including being able to filter. Here we can filter on the question, looking at the view count, like how many people looked at that question. And we can say, oh, we only want to look at questions that were highly viewed, and then apply that filter, and it'll gray out any questions that weren't high, that were scored below 52, since that's where we set it here. And there are many other features as well. So I'm going to delete this feature. You can export CSV file of, and what this CSV file is going to contain is the information from the nodes and the relationships that appear, or you can export a screenshot. I have provided a link. So on this demo slide, if you look at the slides that we're going to provide, there's a link here to Aura. There's also a link to our sandboxes. And then there's a link to learn more about Bloom. There's videos there and far more information about our Bloom visualization tool. All right, so I'm going to jump right into talking about graph data science. Okay, so we just looked at looking at a graph and primarily just looking at subgraphs, being able to find a user, look at what that user asked, looked at who answered that question, looked at tags that are tagged to that question. But once we get beyond that, where we want to say, okay, I want to have a better understanding of my graph as a whole. I want to see how my graph is connected. I want to see who are those most influential people in my network. I want to understand more from a global computation. That's when you want to jump over into graph data science. So Neo4j enables you to use graph data science very easy by providing a huge library of graph data science algorithms from pathfinding and search, centrality, community detection, similarity. These algorithms all enable to ask those broad questions like, what are those most critical points in my graph for a supply chain? Who are those most influential people in my graph? What is disconnected in my graph? Being able to run a community detection algorithm. I'll talk a little bit about this, but thinking about fraud, what are some anomalies in your database? Where are they? Where's a bunch of nodes clustered that shouldn't be? Like, should they be clustered around PII, for example, like something like a social security number? Well, that should be just one person, not multiple nodes. So being able to quickly find those anomalies in your data. And then we also have, as part of our library, graph embeddings, being able to capture that graphiness of your data, or being able to capture some of those scores from these algorithms and in an embedding. And you can use that embedding in your pipelines that you have, or you can use them in our supervised machining pipelines that we have in Neo4j. So for example, we have node classification, link prediction, and this will enable you, and we'll talk a little bit. I think I'm getting a little bit ahead of myself because I'm getting excited, but basically we have the capability of running a graph data science machine learning pipeline from start to finish, pulling out those features that you're interested in using in your model, splitting your train and test data sets, being able to train your models, and then once you've selected a model, being able to store it so that you can run it again later. Another cool feature that Neo4j has to enable graph data scientists is the ability to project a graph. Well, there's a number of reasons why we want to be able to do that. The first would be if you're running an algorithm, if you think about it, if you're running an algorithm like PageRank, because you want to find those most important nodes in your data set. Well, thinking about our data set that we had for Stack Overflow, we had users, we had questions, we had answers, we had tags. But if we just want to know who are the most important people in the graph, well, we don't want to run PageRank on all of our nodes. We just want to project the user nodes and the relationships and other nodes that we need where we're asking that only the nodes that we need to answer that important question of who's most important. So if it's most important based on the questions that they answered, then we just want the users and the questions that they answered. So we want to just project what we need to do the calculation. And then that way it's more performant for that algorithm and increases the accuracy of that algorithm. The second reason why we want to do this is for that very reason, because we don't want to mess up. We want to only project what we need for that algorithm, because that algorithm is going to run a specific way to answer that specific question, and we don't need the extra noise in our graph. Another benefit of being once we've projected that graph and say we did run PageRank and we have these awesome PageRank scores, is you can, yes, write those PageRank scores right back to Neo4j, but because you have this graph in memory, it's also mutable. So if you don't want to write those PageRank scores right back to the database, you actually want to use those PageRank scores as a weight for another graph algorithm, you can do that. You can store the PageRank scores right in the mutated graph and then be able to run additional algorithms using that score and then writing back those scores when you're ready to later. All right, so so with the graph data science library and all of the features that we provide, a lot of data scientists find it very helpful to be able to use Neo4j graph data science library. We could see here there's an arrow pointing to machine learning development. That's because, yes, you want to be able to now pull the graphiness of your graph, whether you're pulling it because of an embedding or being able to pull some of the scores, like perhaps you've identified a community that your users belong to, you want to pull that into your machine learning pipeline, or you want to pull the data from the scores from your centrality algorithm, you can pull that into your machine learning pipeline, because all of this is adding more data to a machine learning pipeline that you have, potentially increasing the accuracy of those models. Or you can pull some of that data into Neo4j and use the graph embeddings to complete your machine learning pipeline using the machine learning pipelines we have available right in Neo4j without having to pull your data out. Another place that's not shown here is also doing your exploratory data analysis. So using some of those algorithms to also have a better understanding of your data, being able to see those disconnected nodes, being able to see those highly connected nodes in your database. Getting that kind of understanding can help also further down the road. Right. Cynthia mentioned a number of different connectors and drivers that Neo4j has. Specifically for data science, we also have a Spark connector, but we have this Python client here, called Graph Data Science. So what Graph Data Science does is enable data scientists to more easily not only write queries to read or write to Neo4j, but also be able to very easily project their graphs and run graph data science algorithms along with the machine learning pipelines right in your Python client. So if you're using Jupyter Notebook, or I've even used it in Spark, you can use the Python client to really easily connect to your database and use a graph data science algorithms. And graph data science can be applied in many different use cases. So we mentioned a little bit about fraud, disambiguation. So definitely if you're looking at multiple data sets that may not have the same unique identifiers, being able to use some of the features, use graph data science algorithms, like clustering, for example, to be able to cluster those nodes with like features using similarity as well. Algorithms. Katie's is getting ready to talk about personalized recommendations, but you can also use it for life sciences, master data management, maintenance, cybersecurity, finding those attack paths, and what are those most critical assets that you want to protect. So there are many ways that you can apply graph data science graph in the real world. And I believe that's it. So I'm going to hand it off to Katie to show you how graph data science can be applied using graph data science for recommendations.
Thanks, Sid. Can you see my slides?
Yes.
Excellent. So yeah, I'm going to dive a little bit deeper into how we can apply some of these graph algorithms to our benefit, specifically focusing in on personalized recommendations. And to do so, I'm going to be using a case study from a large online retailer that we worked with. And before they moved to a graph-based approach, this particular organization was using a collaborative filtering in order to power their recommendations online. And the reason why they chose this approach was because they wanted to take advantage of their historical data to be able to find those similar customers who had similar purchasing behaviors. And then also be able to predict future purchases as part of their recommendation system. So this was going to enable them to both find products that were commonly purchased together and also find those customers that had similar purchasing habits. So for example, in this particular case, if Mingo and Jane both bought the same lamp and Jane also bought light bulbs, then they were able to recommend light bulbs to Mingo as an additional product. And this worked pretty well for them at the start. But as they grew and their data scale grew, they began to run into some issues. So the first challenge that they encountered was the cold start problem. So when they added a new product to their portfolio, like a high efficiency light bulb, they didn't have any past interactions with that particular product in order to be able to bootstrap those initial recommendations. And the same thing was true if they had new shoppers logging on. They had that same problem of not having historical data to be able to find those other similar customers to leverage. Another problem that they had was that they weren't actually able to leverage all of the data that they did have about the customers because it was stored across many different tables. So for example, they might have had in another data source some knowledge that Mingo and Aditi were both interior designers because they both took a course that was offered in collaboration with this retailer. Whereas Jane is actually a contractor who has a contractor account with the organization. And so they know that she is somebody who has multiple large scale projects that are going on at the same time at any point in time. And so even though Mingo and Jane bought the same lamp, they're really, really different personas in terms of how they might purchase future products. And so being able to rework your model to be able to include these different types of enriched views and taking into account this additional context was really challenging for them. And then the final problem that they encountered was just simply scale. So as their portfolio grew to several million products, they encountered an unlimited ability to be able to actually improve the search relevance and the recommendations relevance for their users due to really sparse and heterogeneous data. And that's because when you have so many products, what happens is that your most active customers may only interact with a few hundred products, somebody like Jane, who's the contractor, whereas the large majority of customers would only purchase or interact with a few products each month, making it really hard to have enough of that relevant data in order to drive the recommendation system. So we tend to see this hit in performance with personalized recommendations when we are taking these more traditional approaches, when we have these really high dimensional and sparse data sets. And that's because when we do have this wealth of product options, with millions of products, but only a handful of purchases per customer, each customer's history is going to be extremely unique. And then if you consider how to think about recommendations also from the perspective of trying to increase search relevance, then the challenge is just going to get even worse and your data is going to show even more sparsity. And that's because we're adding another element here. And that's the fact that people are really, really bad at actually matching what exactly they're looking for to how they're describing the product that they're looking for. And so when you're trying to match a search term to a product, you are encountering a lot of really unusual or novel search terms that might not be in your product catalog. So this could just be because people are generating typos, or they're just being extremely creative in terms of what they're looking for. So as an example, during COVID, I found myself having invested in way too many houseplants. And so I was online searching for products that I didn't necessarily know the name of because I wasn't used to being that much of a plant mom. And so instead of using, and so what I was looking for and typing in was stuff like vacation plant watering automatic thing, instead of what the product actually was called, which is a glass watering globe. And so these are the types of challenges that are really hard to approach when we do have these kind of sparse and high dimensional data. And this is where focusing on the relationship between data, so the relationship, for example, of how I'm searching and the search terms I'm using to how I'm actually interacting with the products after I've searched for them and in browsing, can really help improve the performance of your recommendations. And this focus on relationships and bringing together all of the context and all of the information that you really truly can gather about your data or your interactions, your customers or whatever, this is what graph data science is all about. So when you think about data science from a more general perspective, it's not just all about tuning models. We have data capture and exploration, we have feature engineering and experimentation, and then taking those insights that we've been able to capture and delivering them in a production environment that has a supervised machine learning model. And so we've been kind of mirroring that journey a little bit today in this presentation, focusing on relationships in each step. So with Cynthia's introduction, we focused on this first step of really trying to create a knowledge graph. So focusing on data capture and the exploration of that data. But what we're capturing is the relationships and the patterns within those relationships. And that allows us to do is then explore and enrich that knowledge that we have by adding additional layers of inferred relationships based on the patterns that we can then discover within the data. And we can do that using Cypher, and we can also do that using our graph algorithms, as Sydney was talking about. So we can apply these algorithms to extract that additional knowledge, and then we can take that and take that insight and use those as input features to enhance our machine learning analyses. And so we can, as I mentioned, we kind of call these graphy features or this process graph feature engineering. And this is, I do want to emphasize that this is not an either or situation, it's an and situation. So you can also, when you're thinking about training a supervised machine learning model, that's going to be either classifying the data, predicting links between it, or trying to anticipate the value of a property, for example, or any other element of the data you're trying to predict. You can also leverage those existing features that describe your data points in addition to these graphy features. So it's really a supplement to your existing processes. So I'm going to walk through this now, the same problem, taking this approach of those 3 steps in our graph data science journey. So we start off with our knowledge graph, where we can really capture all of the information that's representing our online shopping data, or that experience. So in this case, we have our browsing sessions in pink, the past purchases or our interactions with products in purple, the product information such as brand in blue, and then the search terms that were used in each browsing session in green. And so when we're bringing all of this data into the knowledge graph, we're able to connect all of this, what would have been really heterogeneous information that would have been spread across many different tables. So we've again got the browsing sessions, product information, customer information, and then relate them to each other with these different relationship types, has session, attended, purchased, belongs to brand. And then capturing the data in this way makes it both really simple to query it and traverse the graph to do things like say, okay, what particular search led to a product purchase, resulted in product purchases. But where the real power of the knowledge graph comes in is when we can start to infer additional information. So go beyond just traversing the information that we already know and start trying to supplement that information based on patterns that we can detect in the graph. And so again, one of the ways that we can do this is by using graph algorithms. And I think I might have to speed up a little bit here, so forgive me if I start moving a little faster. So if we take into account those initial challenges that this particular organization encountered, and now think about it from a graph perspective, we can leverage more information for more positive outcomes. So for example, with the cold start problem, where we're adding a new product like that high efficiency light bulb to our catalog, we can use things like similarity algorithms or node embeddings to identify those similar and correlated products. And then we can use those derived relationships to further bootstrap and improve recommendations for new products to our customers. Or they can simply help surface new products as results for search terms that typically result in interactions with other closely related products. And then we can further enhance recommendations by bringing in that additional context for our customers in this case. So we can run community detection algorithms to capture links between similar users and then create those more accurate communities or cohorts. So this allows us to identify that Mingo and Aditi are in the same community and have similar behaviors. And so therefore, now that we know that they are more similar than Mingo and Jane, we can leverage their histories respectively to improve recommendations for each other. And then given this ability to reduce the dimensionality and infer these new relationships and kind of enhance our graph with new information, then our context-driven recommendations are able to continue to give higher and higher quality recommendations, even as your data is growing and changing, because we can adapt, we can pull together these relationships between the data. And it also helps remove the pain of joining many tables, which eliminates data replication and redundancy that occurs as a result of these joins. And so that might work, keeping all of this information separate and then joining together when you do have these questions might be tolerable at smaller scales. But as you bring your analyses into with larger and larger scales of data, then it can be quite cumbersome and challenging. So as we put all of this together, what does it look like? So first, we started off by capturing all of those customer interactions within the graph. So we were able to connect those browsing sessions to products, to product information, and so on, and then represent those different relationship types to capture whether or not it was a purchase or simply a browse or an add to cart and so forth, and capture that those various types of interactions. And then once we have this knowledge graph, then we can start learning customer preferences by analyzing their previous purchase history and using graph traversals to find those similar products purchased by similar customers. And then in the case where we do have these really sparse data sets, we can query them really efficiently to collect really representative information about customers. And then we'll add in those graph algorithms where we can segment users into communities using community detection and run similarity analyses on our nodes and node embeddings to identify those pairs of correlated products, as well as other pairs of entities, such as connecting the search phases to the products themselves. And so this allows us not only to find those similar customers, but also find those similar products and which products are related to search queries. And so then the end result is that we have the ability to generate these really tailored recommendations for each one of our customers. And so unfortunately, while I can't show you the customer data, I can show you a little bit about how we would do this with a publicly available data set in a little bit more of a simpler approach. But it still illustrates how you can take advantage of some of the contextual information in your data to improve these recommendations. So the data set that we're using is the Microsoft News data set, or the Mind data set, that's specifically designed for recommendation research. And so it consists of users and then their interactions with news articles, which belong to different categories. But we're going to really focus in on those users and how they interact specifically with those articles. So, oh, I didn't mean to stop. I meant to just change applications. So I'm going to be doing a very quick demo so we have time for questions. Using Neo4j desktop. So this is another free option if you're wanting to play around with graphs a little bit, that's running locally on my laptop. And so when you think about what Sydney demonstrated using Neo4j Aura, which is the fully managed option, she showed you the query and explore tools. And so in this case, we can translate that to the browser, is what we would call this when you have a self-managed version of Neo4j or the desktop version of Neo4j. So it's the same interface. So let's look at a particular user within this data set and how their recommendations change as we add context to the graph. So I've got a query where I'm looking for the history of what this particular user clicked. And so we can take a look at the articles that they interacted with, and we can see that they like articles related to, automobiles, news and finance, And we're going to start off by taking an approach of just looking at what would happen if we just use classic collaborative filtering in order to generate recommendations for this user. And so you first off note that it takes a second to return. And I'm not actually returning the list of recommended articles. And that's because you can see that there are 63,000 like users based on this user's 6 clicks. And that leads to nearly 11,000 potential recommendations, which is really untenable and not very helpful when we're thinking about trying to have more targeted recommendations. And so it's neither scalable nor personalized. And so we're going to use node embeddings and node similarity, or a similarity algorithm to improve this. And what we're doing with node similarity, so I'm not running that here. I'll show you how we run that in just a minute. But what we're doing as we're creating these node embeddings is really capturing the neighborhood around each one of these articles. And by that neighborhood, we're really capturing how these users fall with between each of the articles. So we're capturing the context and the structure of the graph around each node, and then collapsing it into a vector that essentially represents the shared readership of each one of these nodes. And so we can take a look at the output of that. So this is what those embeddings look like. And so we write these out as properties onto each one of our news nodes. And then we'll run k-nearest neighbors using these embeddings as input features to try and find where are those similar news articles. So we're making the assumption that if these embeddings are close to each other in vector space, then they're also going to be close to each other within the network space. So the result of that is that we can then write out these users also liked relationships. So this is how we're enriching our graph using those node embeddings and the output of our k-nearest neighbors algorithm. So now we can leverage these new relationships as we are developing our recommendations. So now, again, if we just run a similar query using collaborative filtering, but instead on those new relationships, those user also liked relationships, now we only get 60 records instead of that initial 11,000. So, or 60 new recommended news articles. And so this is much more focused and manageable, but we can continue to improve this. So one thing about collaborative filtering with this type of enriched graph is that you can easily update and change the query. So you could just take this particular user's most recent view of an article. So we can also capture that timestamp information. And so let's take a look at that article. So we're just looking at the most recent clicked on article by this same user. And we can see that it's an article about the Ford Mustang Shelby GT350 versus GT500, which is the better sports car. So they're currently showing interest in sports cars. So now if we base our recommendations on just that one article, now we can get those really, really targeted recommendations. So here we have just 10 recommendations that are related to that article based on our enriched knowledge. And you can see that they're extremely relevant. They're, comparing Mustangs to another version of a Shelby GT, which are the performance cars of the year, and so forth. And this is nice because this allows you to basically update your recommendations as people's interests change. And then it results in really relevant articles and really fast queries, because we're just traversing those relationships that are already persisted in our data. And so it's a very, very fast response time and a very scalable approach. All right, I'm going to hop back to the slides. Oh, I lost them, I guess, when I accidentally stopped sharing. Oh, there we go. So making a very few changes in our graph really improved the outcomes of our recommendations. So we didn't actually change the data that much. We just added this kind of relationship between our news articles, saying that the users also liked them. And I could go into this in a lot more detail, but there's a really good blog post that uses this particular example and steps through some code. So I'll recommend that you check it out, but I'll give you a little bit of a teaser. It includes a Jupyter notebook that goes through all of the steps that I just mentioned, including how to run those graph algorithms that we used. So this is just a little teaser of how you can use the graph data science Python client, both to run Cypher, just to repeat those queries that we saw in the browser, as well as run the these fast RP node embeddings and k-neighbor neighbor similarity algorithms in order to create those new relationships. And so this steps you through how to do a graph projection and run the algorithms. As Sid was talking about, this is kind of some of the cool guts that are part of the running graph data science on a graph database. So hopefully today you've been able to understand a little bit of the approach and how you would go about thinking about solving your own graph data science problems. So you always want to start about capturing all of the knowledge, all of the facts that you have about your data, exploring it, finding those additional patterns and enriching it and doing feature engineering. And then you can feed those into more supervised machine learning pipelines. And so then we also have some resources for you all. So we've got some training if you're interested in learning more. We've got in multiple environments where you can get started on your own and build out your own databases. Feel free to join our community, and then you can check out upcoming events with this QR code. And here's even more, and this is a little bit smaller text, but this is more of a leave behind for you all, because we're happy to share these slides. So thanks so much for your attention, and I think I'll hand it back to Yolande to help mediate the questions.
Oops. Yeah, I'm back. If you just move to the questions, I added them to the slide deck. There we go.
Okay, and I do think there were more in Slido as
Yes,
well.
I added a second slide. They're all in there.
Okay, great. All right, it's updated. Okay.
Mm-hmm. Okay, so interview questions. Do you want to do this one, Kiri?
Sure. So I hate to say that it depends a little bit, obviously, in terms of exactly what role you're going into for graph data science, because it is a little bit more of an emerging field. So you could be expected to be quite the expert on graph theory, or you could be expected to be more of a data scientist who's aspiring to expand their skills in graph. And so that's the kind of general advice I would give you, is that to think about interview questions related to data science, as well as potentially graph theory, and thinking I know that I typically like to ask kind of a give you a scenario and think about, okay, how might you apply graph algorithms to that particular scenario and data challenge. But some other questions that might come up might be explaining different types of graph structures, thinking about how specific algorithms work. So you might get asked, what's a breadth first search versus depth first search for graph or different pathfinding algorithms. How to detect a cycle in a directed graph could be potentially one. And then we can share some more resources, I think, in the chat if we have them.
Yep. Sure.
All right. Then where to practice my skills in graph data science? That's a great question. So again, we have multiple options that we demoed today, as well as we'll link for you. So we've got the Neo4j sandbox, which has preloaded data sets. We also, and so that gives you a free instance for a week to test out either the database or the graph data science component with the database. We also have Neo4j Aura, which is our fully managed database offering. And you can do that for free if you're just testing out a small data set within the database. If you do want to run the graph data science algorithms, that is a paid version of Aura, or you can use Neo4j Desktop like I demonstrated today as a free option to just get going and test it out yourself locally. And then we also have online training. So if you go to graphacademy.com, that's a really good resource for just learning more. And there's also interactive exercises as part of that training, which are fun. Okay, what should I learn to help me understand graph data science? Again, it's kind of a combination of data science. So in terms of the approach and a lot of the exercises that you're doing on a day-to-day basis, and the overall skills, it's really similar to traditional data science. But you also have graph theory mixed in there. So trying to understand graph algorithms and more about some basics of graph theory is a really good place to start. What kind of projects can I do? Free data sources, really anything where there's relationships. So classic examples are, social networks. You saw Stack Overflow data. Thinking about, I've worked with people who, took in band tour data and put it in Neo4j, and I tried to predict links between songs and like set lists that were going to happen. So you can really, anywhere you're looking at relationships, or if you have data sets that you need to join together, multiple kinds of information, then you can start thinking about ways to apply graph data science. And then we'll paste a link in the chat. I think I have the link for some graph data sets that you can leverage as well. Do we have that link
Yeah.
handy?
Yes, I do.
Thank you. Coding language, if you're using Neo4j, then it would be Cypher. Depending with other applications or databases, there might be a slightly different version of a coding language, specifically to query the database. GQL, or graph query language, is kind of a developing standard that's highly based on Cypher. And then Python is also handy. You don't have to know Python, but as a data scientist and thinking about data science environments, then I would recommend that as well. And I don't know if I understand this last question. So maybe somebody could comment in the chat to clarify what they mean or what they're looking for with that last question in terms of getting a heuristic for pathfinding algorithms. Maybe I'll move on to the second one.
I could do the first.
Yeah.
So I actually learned how to query Neo4j using Java before Cypher. That's a fun fact. I would recommend, I just put a link in the chat for graph databases for beginners, but if you scroll, it talks a little bit about graph databases, but if you scroll down to the bottom, there's an opportunity to get a PDF of the graph databases book, but basically just getting an understanding of how to think about your data as a graph. And then we do have the Java drivers, but I do suggest eventually learning Cypher because I did find that there were some things that were better done in Cypher than in Java. So, and you can use Cypher in your Java code. So, so definitely just starting with getting an understanding of graph and graph databases first is a great way to get started.
And I'm adding also, so we have a developer advocate that is also focused on Java. So I'm adding also like articles that she wrote and her contact information. So because she is always like demoing different use cases, also more focused on Java.
And then I guess, Katie, if you want to do the second question.
Yeah, that is also an it depends. Because when we're thinking about solving a particular data problem, then each of the decisions that we make when we are both creating the data model as well as defining these properties, so setting a weight on a relationship, then it's going to have some sort of meaning to it. And so that could mean a negative cost, that could mean some sort of penalty, or have a kind of a relationship exists, but it's a negative one. So it could be some sort of sentiment representation. And so it really is dependent on the context. And then it's also important when you're thinking about how to generate these weights, to think about which algorithms you're going to want to apply if you are wanting to apply algorithms on your data, because based on the algorithm, it may tolerate negative weights or it may not. And so you might want to instead scale your weights from on a 0 to 1 scale, for example, or it will depend on the specific algorithm.
So books, so we have actually a website with a lot of books. So let me share this. Oh. And we're raffling 2 books. So those are the new ones. So don't, if you forgot to enter your name there, it's good time to do that.
And I don't, so we do have some good books on graph algorithms in terms of specifically comparing the similarity of 2 separate graphs. I don't know of any books that cover that topic in particular, but I do know there are quite a few more academic articles that cover that topic. And so a quick Google search can get you some of those articles.
And for the tools ideal for working with Neo4j, I think you might be thinking of Tinkerpop, maybe. I believe that's like a graph tool, being able to kind of create a graph out of your data and query it with Gremlin. And I do not think that that's a native graph database. I don't know that much about Tinkerpop, but tools ideal for working with Neo4j. There was a couple of slides that Cynthia went through where she kind of talked about like different connectors and such, that if you're trying to pull data out of Neo4j or import data into Neo4j, there's a lot of tools, but Neo4j itself is a native graph database. It has a query language, Cypher, that you could use to query the database. We have different visualization tools. We showed you Bloom, but there is a blog with lots of other visualization tools, and there are lots of products out there like Linkurious, GraphAware, Xbarrow. There's a lot of companies out there that have built like custom dashboards and other tools that sit on Neo4j for specific use cases like fraud, for example. So there's lots of information of things, tools that work with Neo4j. I hope that answers that question. And also with Databricks, there's a Spark connector that you could use with Databricks. Neo4j is, like I said, a graph database, so you can connect, you could install the Spark connector and then be able to query from Databricks, pulling data into or out of Neo4j, and then being able to use that data out of Neo4j for any processes you have, or being able to, a lot of people use Databricks to clean their data and then push it into Neo4j. You could do that, and then be able to pull those graphy features back out of Neo4j. So hope that answers that question as well.
I think that's a duplicate of the above question. So I can use SQL in a graph database. If not, what language to use for querying? Sydney, do you want to take that?
Sure. We're using Cypher. There are other graph query languages out there like Gremlin and others. I do believe Cypher is far more easier to use than some of the other graph query languages out there. It is, I don't know if Cynthia, you remember, but Cypher query language is going to be used as a standard. They're working on a standard graph query language, and they're going to use a lot of the features from Cypher because it's a really easy graph query language to learn. It has a lot of features, and it's really good for querying a graph database or graph data graph data.
Yeah, the new and upcoming standard is called GQL, and GQL takes a lot of features from OpenCipher. So there is the language Cypher of Neo4j is I wouldn't say proprietary, but there is also an open version of it called OpenCipher, and OpenCipher is the basis for GQL, which will become one of the first ISO approved standard query languages since SQL. So it's been a long time since they've created another ISO standard.
Okay. So the last question, can Neo4j solve traveling salesman? And I'm guessing maybe this is referring to a use case or a joke.
I think it's referring to optimized paths. So you can use the pathfinding algorithms to approach that problem. I'm not super deep on all of the parameters involved, but certainly you could approach it from an optimal path perspective, which we do support within Neo4j, where you can find the least costly route given some certain parameters and weights. So you could, you can definitely try it. I haven't tried it myself, but I'll look more into that specific problem.
Cool. So I think we went through all the questions.
Right.
So any last minute thoughts, questions? A couple more minutes. No? No?
Awesome, no worries. Thank you. Thank you, Katie, Cynthia, and Sid for speaking with us today. You dived into graph data science and knowledge graphs. You showed us a demo of the Neo4j Workspace that allowed us to visualize the relationships and the structures within data and how one could interact with the queries visually. And you also let us know about Neo4j's library and graph algorithms, machine learning, modeling, and visualizations to improve predictions and discover data insights, such as like what's important or unusual, and just adding context to the data. So thank you for sharing that. Just a reminder for everyone to get free online training and certification through Neo4j. The information was shared in the chat along with other additional resources during our Q&A. You can also connect and follow Neo4j. We also left the information in the chat as well, but you can always look up their handle, which is Neo4j. And don't forget, you do have the opportunity to win an ebook from Neo4j. Just enter your information with the link that we provided in the chat, and the winners are going to be selected at random. They'll receive an email with an ebook copy of their choosing. So let's go ahead and move on. For upcoming Women Who Code events, please visit womenwhocode.com/events. You can stay connected with us. Links to our upcoming events and social media and more are through our linktree/wwcodesv. So thank you again, everyone, for attending and have a great week. Thank you to Yolanda from Neo4j and my Women Who Code Silicon Valley team, Jody and Swati, for the behind the scenes support and making this event possible. And thank you again to everyone who attended and for joining us.